So from here, you can directly calculate your stress in the x direction is equal to my over Iyy multiplied by z. Okay. So now I'm pretty sure you can figure out what is your Iyy already. It's straightforward. The confusing part now is what is zz? What is z? Okay. So z now is measured in this direction. Right? So if you mark here, this is your z, z1, z2. Yes or no? Right? So that's your marker. So z is in that direction. So now the z from the centroid, okay, so my will be equal to 60. Z will be equal to 12 times 10 to the power minus 3 divided by 2, right? Because this is your z value. Half it, divide by Iyy, which is equal to 2.88 times 10 to the power minus 9. So this will be equal to 60 times by 12 power minus 3 divided by 2 divided by 2.88 power minus 9. It's equal to 125 plus or minus, right? 125 times 10 to the power 6 Pascal. So what does this mean? Okay, so if I still leave the orientation of the structure still the same, yeah, I'm not going to rotate it. Okay, so what does this actually mean? So based on, so I'm going to draw our transformation, right? So we know that this is our z, right? So based on our transformation, so I'm going to draw, this is our z, right? Then we have a normal stress, right? So this is our z. Okay, so-called over here, this is where our material is, right? And what we are calculating is still stresses in the what? X direction. Okay, so up here now, it's in tensile, still stresses in the X direction. Down here is what? Compression. So I remember we call this I, right? Over here is J, right? So when we look at our vector, sorry, J and K, I do apologize. J and K now, right? So we know that point J is in compression mode, okay? And then tension mode. Okay. All right. So over here is going into compression, pushing into the material, and then tension. So this will be equal to 125, your stress, and the distance now is 0.06 or minus 0.06, right? So this is equal to minus 125, okay, plus by 0.06. Okay, so this is your stress profile. So what did we learn down here? Okay, so this you can see for yourself, right? The difference in value where you either take moment in X or moment in Z or moment in Y. So so in summary, what did we learn? I'm going to draw for you graphically. Based on moment, vector, right? So the head is always in compression. The tail is always in tensile, right? So moment vector. Then for second moment of area, so if this is your axis, right? Anything that is parallel will be known as your width. Okay. Any geometry that is perpendicular is always going to be your what? Your depth. You got this right, you will never be confused. Okay, you got this wrong, that's where you can get really what? Confused. Okay, so these are the two keys. Okay, these are the two keys. What I want you to see today. If you can get this, okay, we're going to apply this, okay, from now up to the end of next week. So if you look at the chapter on bending, is this concept of analysis. It can be for symmetry, unsymmetry, bending. Analysis is the same. Okay, no change at all. Analysis is the same. Okay, that's an interesting part. Okay, right. So next, so far, anyone, any questions, please? Anyone? No? Okay. So let's look at another example. Okay. So let's look at example number 2. Okay. So example number 2, I'm going to copy another diagram. Right. So you have a beam now. Okay, so this is the beam that we have. And then you have 2 vertical forces applied to the beam of the cross section shown. Now we have to determine the maximum tensile and the maximum compressive stresses. Okay, in the portion of BC. So they specify the portion in BC. Now, question for you guys: if this were to fail, where would it fail? Anyone? If this structure were to fail, where would it fail? You all can hear me, right?
Yeah, I can hear you. Not sure where it failed.
Okay, so it will fail exactly in the center. Okay, that's where it's going to fail. So I'm going to call this point over here. Okay, where it's going to break. It's going to break at point E. Okay, where it's going to fail. It's going to fail at point E. Okay, so when the structure deform, okay, the structure will deform this way. So the structure will deform in this direction. Okay, this is how the structure deform. So when that's the case, if we were to draw a transformation, okay, so on the left-hand side is a cross-sectional view. So this is our cross-sectional view. Right? And over the right-hand side is not, okay? It's not. So if I would draw a transformation, this will be X, this will be Y, and over here, this is our rotation in the Z. Right? So on the left hand, the cross-sectional view, this will be my Y, this is my Z, this is my rotation in the X. So we know that for the bending to occur this way, right? For the bending to occur this way, right? Our moment in the Z has to be in this direction. Right? So our moment in Z have to bend that direction. It's like you guys can look at a small screen, okay, where you can see my face or my body. So this is my ruler. I'm going to bend it this way, right? So it's smiling face deformation. So if you look at a structure now, it's also smiling face deformation. For smiling face to occur, you have to bend this way. Yes or no, right? So based on how your moment is applied, so now we know, right, that the top, based on MZ, this will be under compression. The tail end of the moment arrow is going to be tensile. Okay. So coming back to the figure over here, we know that at this tip over here, where I'm drawing, I just draw a circle. This will be under compression. Over here, the bottom part, this will be in tensile. Okay, that will be in tensile. So next, we need to find what is the moment at point E. Okay, we need to find what is the moment at point E. Okay, so the objective of this problem. Okay, so I'm going to tell you what's my teaching objective. Okay, so the teaching objective is I want you to construct your free body diagram. Okay, then we are going to look into your bending moment. Or I'm going to introduce, I know this is still early days, but I'm going to introduce you the shear force. Okay, we're going to look into the shear force. And bending moment diagram. Okay, so there's a lot of component over here. Then after this, after the diagram, we are going to find, okay, we're going to find the centroid and second moment of area. And then finally, we're going to locate stresses at a specific location. Okay, we're going to deal with all this. Okay, so first let's deal with our free body diagram. Okay, so let's deal with free body diagram. Right, so we're going to deal with free body diagram. So this is your X, Y, rotation about Z. So we're going to sketch our free body diagram. So this is our point A, point D, and then point B, and then we have our point C. Okay, so we know that point B and C, you have 10 kilonewton. Okay, and then based on the support, you know that you have AY. So at point A, you have AY, and you also have an AX. Okay, because it is a pin. And then point D, you have only a roller support. You only have DY. Okay, so we're going to do static analysis first. Right, we're going to carry out static analysis. Okay, so we are going to call summation, well, moment Z at point A